Hey everyone, welcome back to another Explainer. Today, we're setting a really sleek, hacker-style terminal vibe because we're about to decode the absolute bedrock of modern computing, the C programming language. And we're going to do it directly from a fantastic set of handwritten source notes that break down these concepts with just incredible clarity. So, whether you're a complete novice wanting to know what makes your computer tick, or maybe an informed enthusiast looking to brush up on those foundations, you are in exactly the right place. Let's get into it. Okay, here's our system boot menu for today. We'll start with the origins of C, then move into variables and data types, hit inputs, outputs, and operators, dive into making decisions in code, and finally wrap up with loops and repetition. All right, Module 1, the origins of C. Before we even think about writing a single line of code, we really need to understand what code actually is. Let's demystify this right out of the gate. A program is simply a set of instructions given to a computer to perform a specific task. Literally, that is it. There's no magic here. The computer is basically just a super fast but incredibly literal worker. It only does exactly what you tell it to do, step by step, using a language it can understand. And the language we're focusing on today, it has literally been the backbone of computing for over half a century. C was developed way back in 1972 at AT&T's Bell Laboratories in the US. It was designed and written by a brilliant computer scientist named Dennis Ritchie. The craziest part is that C is still widely used today. In operating systems, embedded hardware, you name it. It's a real testament to its incredible design and raw power. But here's the catch. Humans write C, and computers read binary. So how do we bridge that gap? The handwritten notes outline this strict, methodical process of how our written source code, which you save as a .c file, actually transforms into a runnable program. First up, the preprocessor handles things like pulling in external files. Next, the compiler translates our human-readable C code into assembly language. Then, the assembler takes that and turns it into machine-level object code. Finally, the linker connects our code with any built-in computer libraries we used and spits out the final executable file, your .exe. It's basically a giant assembly line for logic. Moving right along, Module 2, Variables and Data Types. Now that we know how a program gets built, let's talk about memory. This is where the real logic begins, because to process any information, a program first has to store it. I absolutely love the classic storage box analogy for this. Think of your computer's memory as a massive warehouse full of boxes. A variable is simply an open box with a label on it. As the program runs, you can reach into that box, pull the current value out, and swap it with a new one. The value varies. A constant, though, that's a locked box. Once you put a value inside and lock it up, it cannot change while the program is running. Now, because C is a statically typed language, you have to tell the computer exactly what size and shape of box you need before you even use it. For whole numbers, you'd use an int, which takes up 4 bytes of memory. Need decimals? You'll use a float for single precision, which is also 4 bytes, or a double for double precision, taking up 8 bytes. If you just need a single letter or symbol, a char takes up a tiny 1 byte. And void? That literally means no value. It's just an empty placeholder. Next up, Module 3, Inputs, Outputs, and Operators. Okay, so we've got our labeled data boxes ready to go. The next logical step is learning how to actually push data into those boxes and pull it back out to show the user. To do this, we need to talk to the computer's standard input and output systems. We do this by writing #include stdio.h right at the very top of our program. This gives us access to 2 absolutely critical functions. The first is printf, which lets us print text and variable values straight to the screen. The second is scanf, which actually halts the program and waits for the user to type something in. But, and this is super important, notice the ampersand symbol used with scanf? That is the address of operator. Scanf doesn't just need to know the name of your variable box, it needs the exact physical address in the computer's memory so it knows precisely where to drop that user's input. Sometimes we're going to need to mix those data types, and that brings us to type conversion. C handles this in 2 different ways. Implicit conversion is done automatically by the compiler under the hood. So if you try to save a decimal number into an integer box, the compiler might just chop off the decimal for you. But sometimes you want control. That's explicit conversion, done manually by you. For instance, if you divide the integers 5 by 2, C normally gives you 2, completely throwing away the remainder. But if you explicitly type float in parentheses before the math, you force the program to treat the numbers as decimals, which gives you the correct 2.5. All right, Module 4, Making Decisions in Code. Up to this point, our programs have just been top to bottom, linear lists of instructions. Kind of boring, right? Let's shift into the logic phase, where code stops being linear and actually starts reacting dynamically to the data it processes. Take a look at these flowchart symbols. Notice that diamond shape? That is the decision symbol. When the computer hits an if statement, it looks at the condition inside the diamond and asks, is this true or is it false? If true, execution flows down one branch to run a specific block of code. If false, it just completely skips that block and flows down the other branch. Let's run a quick snippet mentally. If age greater than or equal to 18. Inside those parentheses is our condition. If the variable age holds a number that is greater than or equal to 18, the condition is true. The computer steps inside the curly braces and runs the printf statement. You are eligible to vote. But if the age is 17, the condition is false. The computer completely ignores the curly braces and the user sees nothing. Now, what if things get a bit more complex? This represents a switch conditional statement. Think of a switch statement as a multi-lane highway for your code. Instead of checking a whole bunch of true or false conditions one after another, you take a single variable and provide specific cases for what it might equal. Our source notes apply this beautifully to a simple calculator program. The user inputs their choice, 1, 2, 3, or 4. The switch statement takes that choice and routes the program directly to case 1 for addition, case 2 for subtraction, case 3 for multiplication, or case 4 for division. So if-else is fantastic for sequential true-false checks, but switch is absolutely perfect for matching a single expression against a predefined list of options. But listen closely, because here is the secret weapon of the switch block, the break statement. Without writing break at the end of each case, execution will literally just fall through to the next case uncontrollably. Imagine you picked case 1 for addition, but forgot the break statement. The computer would add the numbers, but then it would immediately subtract them, multiply them, and divide them too. Break tells the computer to jump completely out of the switch block the moment a matching case has successfully finished running. Finally, Module 5, Loops and Repetition. We've reached the final building block. We can store data, run math, and make decisions. Now, let's introduce repetition, for when we want the computer to do what it does best: repeat mundane tasks incredibly fast without breaking a sweat. The first tool here is the for loop. The architecture of a for loop is super elegant because it packs everything you need right into a single line. It has 3 parts. First, initialization, setting up a counter variable, which only happens once. Second, the condition. This is checked before every single cycle or iteration. If it's true, the loop runs. Third, the increment. This updates your counter after the code block finishes executing. A for loop is perfect when you know exactly how many times you want the code to repeat, like if you explicitly want to print the numbers 1 through 5. But wait, what if you don't know how many times the loop needs to run? That is exactly where the while loop comes in. The while loop is what we call an entry-controlled loop. You just hand it a condition, the computer checks that condition before it ever steps inside. If it's true, it runs the code, loops back to the top, and checks again. It does this indefinitely until the condition becomes false. And crucially, if the condition is false the very first time it looks at it, the loop exits immediately and the body never even executes once. So here is the real takeaway. Programming isn't just about memorizing these individual pieces. It's about snapping them together to solve problems. We just saw how a switch statement builds the logic of a simple calculator, running a single math problem based on a user's input. But think about the calculators you use every day. They don't just crash and close after one addition problem, right? So here is a challenge to leave you with. How would you wrap that switch statement inside a while loop, checking a specific exit condition so that your new calculator program runs indefinitely, doing as much math as you want until the user explicitly types an exit command? Think about how these building blocks snap together. Keep experimenting, keep building, and I will see you in the next explainer.